Okay, and I'm going to go ahead and grab a random. Also, if you guys haven't seen, the Project 2 grades are out. Okay, practice problems. And I'm just going to grab a random table from here. Let's go. I'm going to go with this one. All right. So, let's start this off. So again, I'm gonna just skip over first come first serve. That's because that's pretty simple. And I'm just gonna move on to, I guess, shortest job first. I'm gonna quickly draw the grant charts for the 5, and then we're gonna move on to process synchronization. So for the first one, shortest job first, reminder that it is non-preemptive. Non-preemptive, so what does non-preemptive mean? It means that the CPU cannot forcibly take a process, thread, task, whatever you want to call it, from the running state to the ready state. It cannot forcibly release it. Okay. And so that affects the scheduling algorithm. So we're going to start off with shortest job first. And why is it not working? There you go. Okay. So we're doing shortest job first. We're starting at 0. Reminder that shortest job first, what it does, it's non-preemptive and it does exactly what it's called. It takes the shortest job and executes that one first. And if 2 jobs come in at the same time, with the same burst time as well, then you just go with the one with the smallest process ID. So for the first one at time 0, we have at arrival time 0, P1 comes in with the burst time of 3. So we're going to execute that P1. It goes for 3. But while we execute P1 in the queue, we also get P2 with a time of 5, and we get P3 with a time of 2. So again, we're doing the shortest job first, so we're going to be using P3. And that's going to be ran for 2 units of time, so up until 5. And then at 5, there are no other tasks to put in the queue, so we're going to run P2 up until 10. And then at 10, P4, or at 9, P4 comes in as well with a time of 5. And nothing else is there, so we're going to schedule it, P4 for 15. And during that, at time 12, P5 comes in with a time of 5, so that goes up to 20. So I'll just do this. Okay. And that is shortest job first. Any questions about this? Good? Okay. So now we're going to move on to shortest remaining time first. Now, shortest remaining time first is basically just the preemptive version of shortest job first, where it does the same thing. It goes with the shortest job, or the one with the shortest burst time, Is he going to ask for the averages? He may, and if he does, it's just simple. You just add up the waiting times and you divide it by the number of processes, which if you guys want, I can go through making the tables as well, but that might be a bit too long to do for each and every one of them. But just know that when you do it, it's pretty simple. For the finish times, it's just the last occurrence of that process, the number at the end, that's the finish times. For the turnaround times, it's just the finish time minus the arrival time, and the waiting time is just the turnaround time minus the burst time. And so if he asks for the average turnaround time, you would just have to add up the turnaround times and divide it by the number of processes. And if he asks for the average waiting time, you just add up the waiting times and divide it by the number of processes. Okay. So for shortest remaining time first, again, it's just a preemptive version of shortest job first, where it goes with the one with the shortest burst time. And during execution, if a task comes in with a shorter burst time than the currently executing process, then it would preempt. And yeah, that's basically it. If there's a tie, meaning that two jobs come in at the same time and they have the same burst time, again, same thing, just go with the lower process ID. So at time 0, the only thing in our queue is P1 with a burst time of 3. And so we're going to run it. But at time 1, we see that P2 comes in. So I'm going to put our running queue over here. This is P1. And currently, P1 has 2 units of time left. But P2 comes in with 5 units of time left. Okay. So P2 came in with 5 units of time left at time 1, but P1 is still shorter, so it's going to continue running for 2 more units of time up until 3. Okay. Once it gets to 3, it's finished executing, but at 3, P3 comes in with a burst time of 2. And so we see, okay, which one has a shorter burst time, P2 or P3? Obviously P3. So we're going to put in P3 and let it run up until it runs out. So 3 to 5. Okay. Once that one is done executing, at 5, the only process in the ready queue is P2. So we're gonna dispatch P2, and we're gonna dispatch it. We're gonna execute it until 9. So P2 is in the ready queue up until 9. We're at that point only has 4 left. Oh wait, no, sorry. Only has 1 left. Because 5 to 9, that's 4. At this point, at 9, another process comes in, P4, with a burst time of 5. And we say, okay, which one has the shorter burst time? Obviously P2. So P2 is going to finish running up until 10. Okay. From here at 10, the only thing in the ready queue is P4. So P4 is going to get scheduled. And it is going to run up until 12. And at 12, this should be at 3 now. And this one, we see that at 12, P5 comes in with a burst time of 5. And we say, okay, which one has a shorter burst time, P4 or P5? Obviously P4, because this is 3 and this is 5. So P4 is going to continue for 3 more units of time, so up until 15. And then finally, the last thing in the ready queue is P5. and nothing else gets scheduled. So P5 is going to run for 5 more units of time up until 20. Okay. And so this was shortest remaining time first. Okay. So any questions about this? Sorry, someone's typing. Is it fine if we? Oh no, this is someone not in the call. Okay. All right. So that is shortest remaining time first. Next, we're gonna go on to. Let's go on to round robin. Okay. And so again with round robin, we have a time quantum, and depending on the time quantum, it's going to affect the scheduling, right? So again, if the time quantum is too large, it's basically just going to be a first come first serve. And if the time quantum is too small, you're just going to have a bunch of rapid context switching. And so for this one, our time quantum is going to be 1. So very small. Okay. And so there's going to be a lot of computations we're going to have to figure out here. So it's going to be our queue. This is our running queue. Ready queue, running queue. So at time 0, the only process in the ready queue is P1, the burst time of 3. So this is going to run for 1 unit of time. Why 1 unit? Well, again, the time quantum is 1. So even though it has a burst time of 3, it can only run for 1 unit. So when it's finished running, it's going to have a burst time of 2. Okay. Now at 1, P2 comes in with a burst time of 5. And notice I did not like preempt or put P1 into the ready queue before putting P2 into the ready queue. Always while you're doing round robin, or for any scheduling algorithm, put your processes into the ready queue first and then worry about preempting. Okay, because or else you'll mess up your ordering. So we finished off with P1 having 2 left here. And at 1, P2 comes in, so we need to go ahead. Oh, sorry. We need to go ahead and preempt it. So P1 comes out. P1 had 2 left, and P2 goes in with 5. Okay. So P2 goes in with 5. It runs for 1 unit of time. And so it's left with 4. Right, 4 up here. And at 2, nothing else is in the ready queue. So the only thing we're going to preempt with is P1 with 2. So we're going to have P1 2, and then P2 4 is going to go into the ready queue. And P1 is going to run for 1 unit of time up until 3, where now it has 1 unit of time left. But at 3, P3 gets scheduled with a burst time of 2. Okay. Then P1 gets preempted, and P2 gets dispatched. Okay. And then it's going to execute again for another unit of time. You'll notice above the processes over here, I'm writing like how much time they left off with there. So 3. So here, nothing else gets added to the ready queue, and P2's time quantum expired, so we're gonna do another, so P2, 3. We're gonna do another preemption, and then P3, 2 is gonna come in. P3, and it's gonna run for 1 unit of time, so 5. Gonna have 1 left after doing that, because it was at 2, now it's at 1. Then P1 is gonna come in, with a burst time of 1. It's going to run here for 1 unit of time until 6, and it's going to complete here. So P1 is finished completing at time 6. So we're done with P1. Right over here, P1 is done. Then P2 comes in with a time of 3. It's going to run for 1 unit of time. And once it does that, it's going to have 2 units of time left. The P3 is going to get preempted, run for 1 unit of time. And after running for 1 unit of time, it's going to have 0 left. So P3 is done. P2 is going to come in. So 9, it's going to have 1 unit of time left. And then at 9, you see that P4 comes in with a burst time of 5. So we're going to do a preemption. And P4 is going to come in. P4, 5. Okay. It's going to run for 1 unit of time. So 4. Then it's going to get preempted. With P2, 1 unit of time left. And here, this is where P2 is going to complete because it only has 1 unit of time left. So that's done, and now P2 is done. Okay. Then P4 is going to come in with 4 left. And it's going to go up until 12, so it's going to take out 1. And then at 12, P5 comes in with a burst time of 5. And so we're going to do a preemption. With P5, just P5, 5. And P5 is going to run until 13. So now it's at 4. And then we're going to have another preemption. So you can see how there's like a bunch of rapid context switching when you have a small burst time. We have P4, 3. P4 is going to run for 1 unit of time up until 14. Oh, sorry. That's going to be until 2. We're just going to have 2 left after that one. Another preemption. So P4, 2 is going to come out. And P5, 4 is going to go in. For 1 unit of time. So this will get decremented to 3. 3. Another preemption, so P5, 3. 4, 2 is going to come in. This will get decremented to 1. So now, after the next time this runs, it'll be complete. And then P5, 3. 17. Now it's at 2 left. And then P41 is going to finish here. So P41, P4 goes up to 18. So it completes there. And then finally, P5, 2 is going to go.
And between in time 3, shouldn't you have scheduled P3 in there? Between 3 and 4. You scheduled P2. It should have been 3, right? P3. Since 3 is like the last process that comes into the ready queue.
No, it should not have been 3. Remember, it's a circular queue. So you're moving from the head. P3 was added at 3 at the tail. And at time 3, P2 is at the head.
Okay, I see.
So it should be P2. So then at time 18, P5 gets dispatched to execute up until 19. Its time quantum expires at 19, so I'm still going to note it. Note that there's still no preemption, but I'm still going to note it. It checks to see if anything's in ready queue. Nothing's there. So then it continues until 20, and then that's when it finishes. And then it's done. Okay, so this is round robin with a time quantum of 1. Again, this kind of visualizes the idea that if you have a small time quantum, you're just going to have a bunch of context switching, which is not good. And if you have a large time quantum, it's just first come, first serve at that point. Okay. Any questions about this? Anything I should go over here? Good. Okay. Oh, someone unmuted.
So just to clarify, every time like you add a process to the queue, you add it to the end, right?
Yeah, it's the end. It's a circular queue. So, right. So, like for example, here, what Anas was saying was that at time 3, how it was is we had queue. We had the ready queue and then the running queue. But run. And so how it was at time 3 was that P1 was in the running queue, P2 was in the ready queue, and then P3 came in at time 3, right? And so notice that we didn't take from the end, we took from the head. So you add task to the tail and you take from the head. The left side being the head and the right side being the tail. And so when I preempt, I take P1, I put it at the end of the queue, and I take what's at the head of the queue, take what's at the head of the queue, and I put it to run. And that's why at time 3, P2 comes in.
Thank you.
Mm-hmm. Does that make sense, Anas?
Yeah, actually, like I just completely forgot that you add to the tail of the queue, not the head.
Yeah. Okay. Wait 1 second. Okay. So now, we're gonna do the priority ones. And then we'll move on to process synchronization. Let me just grab a priority one. I'll grab this one.
Just a quick question.
Mm-hmm.
In your notes, it says round robin with priority queue. That's not a. Is it like. Was that a typo on his end, or. I don't know.
So round robin with priority queue, that is another type of scheduling algorithm which you won't get tested on. Yeah, over here. Or you mean priority scheduling with round robin?
Yeah, that's what I meant. Sorry.
So this one is basically saying that you any time that you have two tasks that like come in at the same time, but they have the same priority, basically if that happens, do round robin on them. Right? So if I zoom in here, you see that at time 0, P4 comes in. Oh no, sorry, yeah. At time 0, all these tasks come in, and the highest priority one is P4. So it executes until time 7. And then the next ones are P2 and P3 because they have the same priority and they're both the highest priority. And so you see that it starts to do round robin between them until they finish using a time quant of 2, where P2 has the lowest process ID, so it does P2 first for 2 units of time, then P3, then P2, then P3, then P2. At this P2, it completes, so then it does the rest of P3, right, to complete the 8. And then once it finishes those 2, then it goes back to the normal priority scheduling. So then it says, okay, what do we have next? The highest priority ones are process 1 and process 5 because they both have the same priority and they're both the highest. So we go again, okay, let's do round robin on them again. P1, P5, P1, P5.
Okay.
So this is priority scheduling with round robin. The normal priority scheduling is just like the same thing with the normal non-preemptive priority scheduling. I think that's just the tiebreaker. When you have the same priority, is just the process ID number in that case. And that's about it.
I got it. Thank you.
Uh-huh. Okay. All right. So now we're going to do the non-preemptive priority scheduling. Non-preemptive, again, meaning that the CPU cannot forcefully take or stop executing a task to replace it with another task. And this time, instead of using like burst times, like how we do in the shortest job first, we're using the priority. The highest priority tasks are the ones with the lowest priority number. So, for example, P2 has the highest priority because its priority number is the lowest between all of these, right? So make sure not to confuse that. Higher number does not mean higher priority. Higher number means lower priority. Okay. And so with non-preemptive priority scheduling, you basically just go, oh wait, why is there no arrival times? Hold on. Oh, it says the processes have arrived in order from P1 to P4, P5, all at time 0. Okay. So they're all coming at the same time. Okay. And so we're going to be doing non-preemptive priority scheduling. Now, if they're all coming in at the same time, we say, okay, what's their priority? P2 has the lowest priority with a burst time of 1, so we're going to do that one first. P2. So P2 is complete. And then the next one is P5 with a burst time of 5. So P5, that's going to go up until 6. Okay. So this is done. And then here, P1 and P4, we see we have a tie. P1 and P3, we see we have a tie with a priority of 3. Now, this is non-preemptive priority scheduling. This is not priority scheduling with round robin or anything like that. This is just non-preemptive priority scheduling. So we're going to take the one with the lowest process ID, which is P1, and we're going to run it. So P1 runs for 10 units of time up until 16. And the next is P3 up until 2. So 18. So now P1 is done and P3 is done. And then finally, P4 has the highest priority, with the lowest priority, with a burst time of 1. This isn't 1, but I'm just going to write it 19. Okay. And so this is non-preemptive priority scheduling. Okay. Any questions?
We couldn't do
Good.
preemptive on this because there's no arrival times, right?
Yeah, that's true. I'm gonna find another one for that actually. Let's see. Okay, I'll do this one for preemptive. Okay. So this one is preemptive. Preemptive priority scheduling. And so how this works is while you're executing something, if another task comes in with a higher priority, preempt. That's basically it. Right? And then if a task comes in with the same priority as you, I think if it's just normal preemptive priority scheduling, just keep executing. And if it's preemptive priority scheduling with round robin, you do as we said before, you run robin on both of those tasks. Okay. So at time 0, we see P1 comes in with a priority of 4. So P1 comes in. And it keeps running up until, sorry. I'm just running the remaining time here. It keeps running up until until time 2, P2 comes in with a priority of 4 and a burst time of 6. A priority of 3 and a burst time of 6. Okay, so this one has a higher priority. So P1 is going to be preempted with its priority and its remaining time now being 4. And then P2 is going to be put into the running queue. That's fine. Okay, I don't know why that's happening. Okay. So P2 is now running, and it's going to run up until time 4, where at time 4, another task comes in, P3, with a priority of 2 and a burst time of 3. And so at this point, P2 ran for 2 units of time, so now it's at 4 as well. Okay. And so here, this new task, P3, has a higher priority than the currently executing task. So we're going to have another preemption. So P2 is going to come out. And P3 is going to go in. So P3, 2, 3. Okay. And so P3 is going to start running. It runs for 3 units of time. So up until time 7. Here it's done. Nothing else came in for it to be preempted, so it's done. And we're good. Okay. Now here we're going to say, okay, what else in the ready queue that we can run? Well, we have P1, which has a priority of 4, and P2, which has a priority of 3. So we're going to go with P2 because it has a higher priority. And so P2 is going to run all the way up until time 9. Okay. It's going to run all the way up until time 9 with 2 units of time left. And at time 9, P4 comes in with a priority of 1 and a burst time of 3. And we say, okay, this one has a higher priority, so P2 is going to get preempted. And P4 is going to come in. So this has a burst time of 3. So this is going to run up until 12. And at this point, P4 is done. And we're good. Then we say, okay, what's left? We have this task with priority 4 and this task with priority 3. We're going to go with the 3. So 3, P2, 2. And so this one is going to run up until 1 unit of time, so 13. Where here, another task comes in, but it has a priority of 5. So P5 is a priority of 5 with the burst time of 3. So the 2 tasks that are in the ready queue right now, they both are higher priority or lower priority. So we can continue executing P2. So P2 is going to continue executing up until 14. And that's where it finishes. So P2 is now done. Let me say, okay, what else in the ready queue? P1 is there. It has a lower priority than 5. So I'm going to put in P1. It's going to run for 4 units of time. So up until 18. Here it completes. And then P5 is in here with a burst time of 3. And so this is going to run all the way up until 21. Okay, so 6, 12, 15, 18, 19, 20, 21. So it confirmed that it should go up to 21. If you add these up, if it's equal to 21, then we did at least something right. Okay. So it looks like we were able to execute everything, and that should be good. So this was preemptive priority scheduling without round robin. If you want to look at how round robin works, which I don't think will be tested on that, it's right here. Okay. I don't think I have normal, not preemptive priority scheduling on here. Oh, I think, yeah, I have one right here. So if you want to take a look at that, you can as well. All right. Do we need to put the dash between P2 and P2 if it's just P2 being ran? I like to, but you don't have to. I don't think. I like to put like a dashed line, but you don't have to put anything at all. I just put that there like while I work to kind of see what I'm doing, and then I can use that to check my work again and stuff. Okay. Someone's typing. Yeah, it doesn't get interrupted. Again, the dash line is just me checking. The actual like full line, that means that it was interrupted. So yeah. Okay. So that's pretty much it for process scheduling. Any questions about anything we just went over? Anything at all? Or are we all set?
I mean, do you think he's gonna give like anything like trick wise on this, or is this kind of how simple it's gonna be?
I mean, I think the main trick that he may give is like with like round robin, for example. Like he might trick you by like trying to trick you into preempting the process before like putting the incoming processes on the ready queue so that like your processes get jumbled up and then like it's just not in the right order anymore. That may happen maybe. But I don't see how else he can really trick us. That like there's not much else to it. This is pretty non-trivial. Shamir, you have a question?
Yeah, I was just gonna say, I wanted to look over number 38 because I got confused with that. I didn't really know how to like approach it because that sort of question, I didn't really like.
Oh, this I haven't even looked at this. I skipped it because I was like, if he's giving us like these kinds over here, I doubt he's gonna give us this too. Let me see what this is. Consider the following set of processes with given CPU I/O burst times. The processes are assumed to have arrived in the order P1, P2, P3 at all time zero. Assume that P1 is the highest priority and P3 is the lowest priority. Assume that the I/O operations cannot be done in parallel. That is, if a process is doing I/O, other processes must wait until the current process finishes its I/O operation. The I/O scheduler uses FIFO scheduling. Draw a Gantt chart illustrating the execution of these processes using priority scheduling without preemption. Compute the average waiting time and CPU utilization.
I was just gonna say like I don't know if we like went over this section with him. So I'm like, is he gonna
Yeah, I
ask
don't.
this or?
I mean, I haven't seen us do anything like this in class, so I think it should be fine. Because I don't know what it means by 5 CPU, 17 IO, 4 CPU. I'm not
I'm
entirely
thinking
sure
it
what
might
this
be.
chart is showing.
I'm thinking that like it might be whether it's like a CPU intensive versus IO intensive, and it's just saying that we can't have IO parallel. So if like one, you'll have like one IO process for two CPU processes at the same time in parallel. I think.
No, yeah. Oh wait, I see what it's saying. It's saying that you. Wait, what? Okay, I see. Wait, do I? No, I don't. Never mind. Yeah, I don't think this will be asked. We haven't done any questions like this in class, and if he's already giving us these scheduling stuff like up here, oh, I don't think he'll even ask this either. But if he's already giving us scheduling questions like this, I doubt he's gonna give us scheduling questions like this in like the short answer ones. So I think it's fine. Because I don't even know how to read this either.
Yeah, we can
We've
move
done this
on
in
after
class,
this.
so
I
yeah.
don't think he's gonna ask it either. I was just like wondering if you like knew even what was going on with it at all, cause like
No, yeah, I don't know what I'm looking at.
yeah, that's fine.
Okay. All right, so we can start to move on to process synchronization. I'm just going to touch on a few important parts of it, and then I'm going to hand it off to Lauren to go over the practice problems as well as the molecule problem. I'm just going to quickly cover or skim through mutex locks and semaphores, and then we're going to move on to Lauren. Okay. So process synchronization. Oh, sorry. All right, so what is process synchronization? If a shared resource is being modified by more than one thread concurrently, then unexpected results may occur. By a shared resource, I mean like you can have like a dynamic data structure or things like that. If you have a bunch of threads that are trying to edit it at the same time, then you're going to have unexpected results. An example of this is like the bank deposit problem that he gave, where multiple threads are trying to access the balance of an account, and it's just causing errors when depositing, and it's making the bank money while it's making the user lose money. And so to, I guess, prevent this, we need to synchronize these threads so that one thread at a time is able to access these shared resources. By access, I don't mean like read it. I mean one thread at a time is able to edit it. Okay. So again, the problem is that concurrent threads access a shared resource without any synchronization, and this creates a race condition, meaning that the output depends on timing. And we need mechanisms for controlling access to shared resources when working with concurrency. Okay. First, we need to know, okay, what is shared among these threads? We know that local variables are not shared, so you do not need to synchronize local variables between threads. Let's say you have a thread and you create a variable within its function. You don't need to like create a critical section for that or anything like that. But global variables are shared, and dynamically allocated objects are shared, which that's all stored in the heap, and the threads are able to access it through pointers. So those are things that you need to synchronize between threads. And so to accomplish this, we want mutual exclusion when accessing shared resources. What does this mean? This means that threads are exclusive to one thread at a time, meaning that it cannot be edited by multiple threads at a time. And if one thread is editing a shared resource, the other threads will be blocked from editing that shared resource. Right. So when one thread is using a shared resource, other threads must be excluded from accessing the same resource until the first thread is done with it. Okay. So the part of the code where the shared resource is accessed is called the critical section. This is where I don't want to say accessed. It's probably better to say like edited or changed. It's like it's manipulated, because reading it is fine, but actually like changing it, that's the critical section, right? And so only one thread can execute in the critical section at a time, and all threads are forced to wait on entry, meaning while one thread is executing and another thread tries to come into the critical section, it must wait right before the critical section until the other thread is done. Okay. So here's what the structure kind of looks like. You have your entry code, then you have your critical section, and then you have your exit code, and then you have your remainder section. So the entry code is just like code that isn't affected if multiple threads run it at the same time. Same thing with exit code and remainder section. But critical section is when things do matter. So again, like I said, the deposit problem. This is your critical section, and then your remainder section will be your exit code. And your entry code and exit code would be your actual locking mechanism, which we'll talk about in a bit. So again, your critical section, at most one thread is in the critical section at once. And if thread T is outside the critical section, then thread T cannot prevent thread S from entering the critical section. So no one thread can prevent another thread from entering the critical section if that thread itself is not in the critical section. And if thread T is waiting to enter the critical section, then T will eventually enter the critical section because we don't want any starvation. So you're going to enter it at some point. So there's several mechanisms for synchronization in concurrent programs. Ones that I didn't note here are like monitors and message queues. I think it's, I don't know, there's something about message, something, I don't remember. I didn't put it on this exam review because it's just for exam 2 and it's not going to be on it. That will be on the final. But our two ones that we need to talk about now are mutexes or mutex locks and semaphores. So mutex locks, or otherwise known as spin locks or blocking locks, are a basic primitive for ensuring mutual exclusion in multi-threaded code. So that's what actually that's the mechanism that actually does the entry code and exit code, where it locks, it blocks other threads at the entry code, and it allows other threads to enter at the exit code. And the semaphores are a higher level synchronization primitive used for both mutual exclusion and coordination between threads and processes. So on the exam, I would avoid using semaphores for mutual exclusion. If he's saying to get mutual exclusion, I would try to use mutex locks instead. And then for coordination questions such as molecules or first, second, third, things like that, you would use semaphores, which we'll talk about semaphores more in a bit. We're going to focus on mutex locks now. So again, mutex locks are a synchronization primitive used to protect critical sections and ensuring only one thread can access a shared resource at a time with the following two operations, which we'll talk about in a bit. But again, mutex locks, just to reiterate, they're a mechanism to achieve mutual exclusion in a multi-threaded program. And so the two operations it uses are acquire and lock and release and unlock. So these need to be used like they need to be paired up with each other. So if you use acquire, you need to use release, and if you use lock, you need to use unlock. All right. So acquire and lock, it's a function a thread calls this before entering the critical section, and with release and unlock, a thread calls this after leaving the critical section. Okay. So here's an example for you with our deposit problem. Here in our deposit problem, before entering the critical section, you would acquire the lock, which the lock itself, if it's 0, that means that it's unlocked. So if you acquire it, the lock becomes 1, and then to other threads, that means, oh, someone is using this lock. We can't use it, which, by the way, this is just pseudocode right now. And then when you release it, the lock becomes 1. When you acquire it, the lock becomes 1. When you release it, the lock becomes 0. And then other threads are able to use it. But while you're in the critical section, other threads will sit right here and wait. They're going to sleep right on this line of code right here and wait on the mutex queue, I think it's called. Okay. And so they're going to be spinning on that portion there. That's called a spin lock. And the spin lock has some pros and cons. The spin locks can be implemented in user space, so there's no need to trap to the kernel, and they are useful in multiprocessor environments. But the cons are that they're horribly wasteful in single CPU environments. because if you have just one like program just continuously spinning on a lock, it's going to just be wasting CPU power. Whereas if you have a multiprocessor environment, you can have one thread actually executing the critical section on one core, and then on another core, you can have one thread just spinning on that lock. So it's useful multiprocessor, but it's very wasteful in a single CPU environment. Um, and like I said, if a thread is spinning on a lock, it's simply wasting CPU cycles. Okay, any questions about what I've gone over so far? Good. Okay. So the ideal implementation, which this is how it works in the real world, again, up here is just pseudocode. But the ideal implementation is that when acquire is called, you're going to spin for a short amount of time, like we said. But if you get the lock during this time, you're going to enter the critical section. But if you don't, then you are going to trap to the kernel and sleep in the mutex waiting queue. So again, like I just said, if you don't get the lock, trap to the kernel to release the CPU and sleep on the mutex's waiting queue. What this does is it releases the CPU of like just wasting CPU power, and it allows other tasks to be executed while you sleep on the mutex waiting queue. And now when release is called, if there's a thread sleeping on the mutex's waiting queue, you're going to wake it up, or you're going to trap to the kernel and wake it up. Otherwise, simply set the mutex to 0 and then continue if there's nothing on the mutex waiting queue. And so the real world implementation, what actually does this is the postx pthread mutex functions, which in your exam, you're going to have to code using pthread mutex functions. So like when you're creating a mutex, you'd have to do like pthread underscore mutex underscore t space mutex. That's how you create a mutex, which is what I talk about down here. This is how you create a mutex. This is the data type pthread underscore mutex underscore t, and you're going to name it mutex or name it whatever you want. And to actually initialize it, you have to set it equal to pthread underscore mutex underscore initializer. This is just the syntax. It has to be in all caps. That's how you actually make it so that you're able to use the mutex. You need to set it equal to pthread mutex initializer in all caps. And then some useful functions that you need to know. The lock function. It's the function to lock, obviously. And you just need to pass it the actual mutex itself. It's going to be pthread underscore mutex underscore lock, and you pass it the mutex with an ampersand to the left. And then another one, unlock, same thing, it's the function's unlock, and you just pass it the mutex with an ampersand to the left. Don't forget the ampersand because you might lose points if you do. Okay, any questions about this mutex syntax here? Or like how this applies on the exam?
Just to confirm, for the lock and unlock, it's just that part that you have dash, right? P thread, mutex lock, ampersand mutex, right?
Yeah. So when you want to lock a mutex, you have to physically write pthread underscore mutex underscore lock, and then pass in the mutex.
Right. Okay.
Like if you try to just put like lock parentheses and LeetCode, it's not going to work. You have to actually write this.
Right. Also, for the initializer, there was like a different function that I had used for it. I think it was like the init function. Like pthread.
Yeah, there's that as well.
Yeah, is either fine, I guess.
I would assume so if either one works. Let me bring it up so people know what you're talking about.
Yeah, because that's the one that I think I had on from the from the PowerPoint.
Yeah, either one works. The initializer is kind of easier for me. But yeah, this one works as well. Pthread mutex init. The only difference is that with pthread mutex init, you cannot execute this function within a global space. You need to actually like execute this within like a main function. So that's why I prefer, like, since you're able to set the value of variables in a global space, that's why I prefer to just set it equal to pthread mutex initializer. But you can also just run pthread mutex init and then pass in the mutex itself. What are the other attributes? Do you remember, Lauren?
Give me a sec. I'll pull it back up again.
Is the second parameter just like 0 or 1?
Pthread mutex init ampersand mutex comma null pointer.
Null pointer. Okay, and then that makes it like initially unlocked. I suppose. So I guess that would look like,
yeah,
here,
I guess
can
so,
write it here.
because after that I used it to lock.
So
Yeah.
I will right here. It's pthread mutex init ampersand mutex null. So these two, they do the same thing, setting the mutex equal to pthread underscore mutex underscore initializer. These two do the same thing. It's just that you cannot do this one in a global space. So that's why I prefer to use this one when I'm like actually like coding it on a and I'm gonna expect to compile it. On the exam, I'd assume that he allow you to do this in global space, but I would just ask, or you can just stick to doing this, either one.
Really random question, but how do you do it with the semaphores? Because I used the semaphore in it as well. For it as well for like
So
the
semaphore
code.
init, you can't do semaphore init in global space either. I don't know if there's a way to do it in global space, but for semaphores, I also
I put it inside
did
the
it.
constructor
Yeah,
of like
I
the
put it
method.
in like the main. Yeah, I put it here in like the H2O create function
Yeah.
that gets ran.
I did the
I
same.
put sem init, so I set the semaphores values like that. Because you can't do that in, like, if I were to do sem h and then directly below it put sem in it, that wouldn't work. You can't do that because you can't run functions in global space. Okay. Any questions about the syntax? Any more besides the one Lauren gave? All good. All right. Okay. All right. So this is for just normal mutexes or mutex locking. You can also have recursive locking. So recursive locking, what that is that within a function, within a function that a thread calls, if you in some point in the critical section also call another function, and then you want to have a lock within that function, that's just recursive locking. So it's kind of like you're just calling a function within your critical section that also needs to be locked. That's called recursive locking. I don't think that will appear on the exam. I highly doubt it. But this is the syntax for it. I don't exactly remember it. But this is kind of how it looks. Let's say you have function A, and within function A, in the critical section, you call function B. And then within function B, you also have that's using that same lock. But in order to do that, you need to run, where is it? You need to run this. You need to run pthread mutex attribute set type. And so what this does is you're able to set your mutex to a recursive mutex, and this will allow you to do something like this. Okay. In order to do that, you need to declare an attribute. So it's pthread mutex attribute t. And yeah, I highly doubt he'll like have you code this on the exam, but I guess it's good to know. Okay. Wait for synchronization. Wait, so for synchronization, basically anything from the short answer is fair game, but the only coding question guaranteed is going to be molecules, right? Yep. we'll go over, again, I haven't looked at the short answer yet, so I don't know how it is. So when we go over it with Lauren, it'll be my first time looking at it. So we'll see. Okay. Oh, and I think you would also have to, with that same attribute, instead of putting null for the init, you put the attribute itself. Okay. So that's pretty much it for mutexes. That's pretty much all you really need to know. There's some other stuff here which I doubt he'll ask about. If he does, it might come up in the short answer, which we will see it when we go over with Lauren. But I don't think priority inheritance. Yeah, I don't think this will show up. So now we're on to semaphores. So for semaphores, again, there are a way to one, achieve mutual exclusion, and they're also a way to achieve coordination or synchronization, whatever you want to call it. But coordination is the best way to call it. By coordination, I mean ensuring that while one specific thread is executing, other threads don't execute until that thread executes, and then you continue. To do that, you use semaphores. And again, semaphores are a synchronization primitive that is used for both mutual exclusion and coordination between threads or processes. This part isn't really too relevant, but an integer variable that is manipulated atomically through two operations, wait and signal. I think it would be more, I think it'd be better to put post instead. Where wait, you pass in the semaphore, decrements the semaphore's value and blocks the thread if the semaphore value is non-positive until it becomes open. What does this mean? If the semaphore's value is 0, then all threads that reach the wait function are going to wait on that semaphore. They're going to go sleep. But if it's positive, then it's going to decrement the value of the semaphore and then continue. Okay, so if the semaphore has the value 1, then the wait, and then the thread reaches the wait with that semaphore, it's going to decrement it to 0 and then continue. And then with post semaphore, it's going to increment the semaphore value and unblocks a waiting thread, if any. So let's say some thread is waiting on a specific semaphore, but then another thread posts to that semaphore, increasing its value, then that other thread will wake up, decrement it again, and then continue. Okay. So there are two types of semaphores. There are binary semaphores and there are counting semaphores. Binary semaphores are very similar to mutex semaphores because they can only take on two values, 0 or 1. I mean, what I mean by mutex semaphores, I mean that like if it's 0, it's unlocked. If it's 1, it's unlocked. Or sorry, if it's 0, it's locked. If it's 1, it's unlocked. That's what I mean by how they're kind of similar to mutex semaphores. Where you can use it as a blocking mutex lock. They're kind of like a substitute. Where if it's initialized to 1, if it's initialized to 1, it'll allow threads to pass through. Or you can use it for thread process coordination. Okay. Which this use is not possible for mutex lock, where mutex locks are just used to achieve mutual exclusion, whereas binary semaphores are used for mutex locks, so mutual exclusion and process coordination. Now, counting semaphores, these take arbitrary values that can be like from 0 to n, and it represents a resource with many units available. So you can set it to n, you can set it to n minus 1, you can set it to 0, you can set it to whatever you want. I think just not anything below 0. You can counter initialize to n, where n is the number of available units. What the fuck just happened? Okay. And it allows threads processes to proceed as long as more units are available. So if the semaphore's value is over 0, It'll allow more threads to continue until um, its value is 0. So each wait decrements the counter, and each signal, I'm going to change this to post, increments it. Okay, so here are some important functions. To initialize a semaphore, to declare a semaphore, you say sem t. This is the data type, sem underscore t. This is for C, this is not for Java. So if you're looking to code the exam in Java, this is not the same syntax, but it's going to be sem t, and the variable name is sem. And some important functions again, we have sem init, where for the first parameter you pass in the semaphore. For the second parameter, you're always going to pass in 0 for now. What does this mean? 0 signifies that the semaphores are going to be working with threads in the same process. But if you put in 1 for the second parameter, that means that the threads you're working on are from different processes, which that's like a higher level thing. So just anytime you use sem init for now, just put 0 for the second parameter. So again, first parameter is the semaphore itself with an ampersand. The second parameter is just 0. And then the third parameter is going to be the value that you're going to assign to the semaphore. So here's an example. If you want to initialize the semaphore to be with 0, you say sem init, the semaphore 0, 0. And if you want to initialize it to 1, you say sem init, the semaphore 0, 1. Another example, if you wanted to initialize it to the value n, then you would say sem init ampersand sem 0 n, where n is greater than 0. Or actually, where n is greater than or equal to 0. Okay. Then we have sem wait. Again, wait does what we just said above. It will make a thread wait on that specific semaphore if its value is less than or equal to 0. And if it isn't, so if it's positive, it's going to let the thread proceed, but it's also going to decrement the value of the semaphore. Post just increments the value of a specific semaphore, and then destroy just does what it does. That's what it says. It just destroys the semaphore and makes it unusable. I believe that's what it does. I haven't used it before, so I don't know.
Do we have to destroy it? Because I know like sometimes at the end, like you have the method to like destroy the resource at the end.
Yeah, so I saw this one H2O free. I haven't. Anytime I run this on LeetCode though, I've never put anything in here, so I don't know. On the exam, if he says to like clean up your resources after, then I would say like at the end of your program, just write sem destroy and then pass in the semaphore, or pass in the semaphores that you use. So you say sem underscore destroy ampersand sem, and that'd be it.
All right.
Okay. So here's some use cases. Like we said, you can use it for mutual exclusion. To do this, you're going to declare binary semaphore and initialize it to 1. You're going to call sem wait before entering the critical sections. That's kind of like your lock. And you're going to call sem post when leaving the critical section. So again, sem init, one kind of represents it being unlocked. So you're going to do sem wait right before the critical section, and then sem post right after, right? Because sem wait is going to decrement its value, and then its value is going to be 0 after the wait, and then it's going to become 1 after the post. Okay, use case 2 is providing coordination. So assume you have 2 threads, T1 and T2. We want T2 to run first and print a message. Then we want T1 to continue execution and print a message. To do this, declare a binary semaphore and initialize it to 0, where T1 calls sem wait to stop at the rendezvous point, and T2 calls sem post to let T1 continue. So this is kind of like the first, second, third problem on LeetCode. where you initialize a semaphore to with the value 0, and you have thread wait on that semaphore. You have thread 1 wait on that semaphore, so it can't run until T2 allows it to. So T2 does something, and then once it wants to allow T1 to run, it does send post. That wakes up T1, and it continues and prints whatever. Okay, so that again, that's like our first, second, third problem. Use case 3, allowing a certain number of threads inside the critical section. This is kind of similar to our molecule problem, where assume you have an application where you have 3 resources of a certain kind. You want to have a critical section where there could be up to 3 threads inside the CS at the same time, and the 4th thread trying to enter the critical section must block at the entry until one of the threads inside the critical section leaves. So to do this, you're going to use a counting semaphore. You would set the initial value to 3, and then you would just continuously wait. You have 3 threads wait on this semaphore until its value becomes 0, and then post once you leave, and that's about it. So that's very similar to the molecule example as well. Some final words, and then we wrap up semaphores and mutexes. So there's some things to know: deadlocks and starvations. Semaphores can lead to both deadlocks and starvation if not used properly. What are deadlocks? Deadlocks are if 2 or more processes are waiting indefinitely for an event that can be caused by only one of the waiting processes. And starvation, we know what that is already. It's indefinite blocking, so a process may never be removed from the semaphore queue in which it is suspended. Okay. And then one final distinction that we need to see, the difference between semaphores and mutex locks. Mutex locks, they're used to achieve mutual exclusion, whereas semaphores are more so for signaling mechanisms, but they can also be used for mutual exclusion. The counter value, the mutex locks are always binary, so it's either unlocked or locked, so 0 or 1. And semaphores, they can be 0, they can be 1, so that's binary, or they can be greater than 1, so it's a counting semaphore. Ownership, mutex locks are owned by the thread that locks it, and semaphores are never going to be owned by anything, so they're not owned by a specific thread. Blocking, the lock operation blocks if already locked, and the wait operation blocks if value is equal to 0 in semaphores. Complexity, mutex locks are kind of simpler. It's just single thread access only, where semaphores, you can manage multiple threads simultaneously with counting semaphores. So it's a bit more complex with semaphores. Not to say that it's harder to code with, it just you're able to make more complex programs with semaphores. And the use cases of mutex locks is protecting critical sections, and the use case of semaphores is also protecting critical sections, but it's also synchronization and coordination. And then finally, for mutex locks, deadlock potential. Deadlocks can occur if unlock is not managed properly. So that is decided by the user. If you're not handling properly, then you can cause deadlock. And same thing with semaphores, they can occur if used improperly. Okay, so that is it with mutex locks and semaphores. Before we move on to doing the problems, whether that be the coding or the practice problems he gave, is there any questions on mutex locks or semaphores before we jump into the problems? Any clarifications that need to be made? Give me 1 second. There we go. Okay. Okay. No questions? All right. So I guess, Lauren, do you want to pick it up now?
Yeah, I gotcha.
Okay.
All right, so I did the short response questions. Let's see. Don't mind me sharing my screen. Okay, we good?
Yeah, we can see.
All right, awesome. All right, so I had done a couple of the LeetCode questions. Let's definitely go over the short responses first. Please pardon my about 100 tabs open on my computer right now. It's a miracle that it's working correctly. All right, so first things first, right? Let's go quickly through these guys because most of this was pretty much said by Justin already, so thank you for that. So what is a critical section? What is mutual exclusion? And write a simple code to show how you would achieve mutual exclusion in a critical section using a mutex lock. So again, if you're going to do something, you want to say pthread mutex t. You can call it mute or whatever you want to call it. It doesn't have to necessarily be the name mutex. And I use the init function just because that's like, I don't know why I'd used it, but that's just the way I did it. So I just remembered, it's add ampersand to be a pointer to the mutex and then a null pointer or null. I think either is fine, honestly. So then once this is initialized, right? This is like done like outside, like either in like a like in the main method or like in the constructor for it. So that's honestly fine. And then you have your function here, right? I lock, right? I have the ampersand mutex for that. And once I lock it, then I'm good to do the critical section. So usually this is done with like a G++ or some sort of global variable or non-local variable that we're incrementing, like with the bank balance. And then we just unlock it at the end. And again, critical sections, the part of the code where the shared resource is accessed. So we don't want any non-deterministic behavior happening. So we want to make sure that it stays the way that we want it to always act as. So no unknown behavior. We don't need a race condition. I think there's a question about race conditions, but essentially it's proving that, if one process runs before another, you get a completely different output. It's like a race to the finish line. And mutual exclusion is one and only thread is allowed in the critical section at once. So one thread only, other threads can't access it until that first thread is done. Right? So just like the deposit example, something like that is another example of this. So what is an atomic instruction? It's essentially you want to make sure everything happens in one single step. You don't want to break it down because in the case of, before we had mutexes, right, we didn't want one step to be done and then we get preempted because, again, non-deterministic behavior. And the way that they had it on Intel was called this function, compare and change. You probably know it better as test and set, right? That was kind of pretty much what we have with the spin lock, in the sense that you want to see test if it's locked already. Actually, no, test if it's unlocked, right? If it's unlocked, go in and lock it. Like you're kind of going into the bathroom kind of example. So in Intel, it's compare and change. I'm not really sure why he was asking for Intel, but otherwise you would know it as test and set, which was in the PowerPoint. Oh, look at that. Test and set. What is it used for? So it tests the value of a memory location, right, and sets it to a new value in an atomic step.
In the Intel architecture, is it called compare and change, or is it called test and set?
Compare and change is Intel. POSIX is test and set.
Gotcha. Okay.
I'll write that down. Yeah, so in the PowerPoints, you can kind of see both, but most of the implementation is done with test and set. So you load the memory location and you set it to the new value, right? So you load it initially as 0. It's unlocked. Think of the bathroom example. The bathroom stays unlocked. And then only if the test passes and it's unlocked can you go in, right? That's the test part. If it's unlocked, then you go in and you lock it by setting it to 1. Otherwise, the lock was already set. So that's kind of what we're doing in test and set. Best way of thinking of it is like with the bathroom example. And again, what is it used for? Just to kind of establish that mutual exclusion, right? We want to make sure that only one thread can actually get into that critical section at once. So it's not always the most optimal, because you're spinning on this test condition all the time. But so, oh wow, I'm predicting the future here, I guess. Briefly explain why spin locks are not appropriate for single processor systems, yet often used in multi-processor systems. So it's very wasteful, right? What is a spin lock doing? It's spinning on that test condition. So you're literally wasting CPU cycles because you're just constantly testing, like, hey, are you done yet? Are you done yet? Are you done yet? Once again, bathroom example, right? But on a multi-processing unit, it's actually very efficient because if you're constantly polling, in a sense, to see if that resource is able to be used, the other thread can acquire it immediately as soon as it gets dropped. So as soon as that key gets dropped, it's like you don't have to worry about like wasting any CPU cycles, and you just take it immediately. You can think of it as like when we do process scheduling, something's right on that ready queue, and you can just take it immediately. So what is a race condition? As I said before, when the behavior of a system depends on the sequence of events. So when you have different processes or threads that are sharing resources, you could have non-deterministic behavior in the sense that the different order results in different results. It's a race. If thread 1 finishes first, maybe something happens, and then thread 2 finishes first, something else would happen. We want to make sure that it's always deterministic. We can determine what's going on. So that's the main thing with race conditions. So list 4 requirements of a critical section, right? We want to make sure mutual exclusion, only one thread at a time. And that prevents race conditions from happening. We also want progress. We don't want deadlocks. We don't want starvation. So because of that, we need to actually be able to progress through the critical section. You can't go in the bathroom and hide there for the entire day, unless your name is Poe. So then the third condition, no starvation. So you don't want to have threads wait indefinitely, right? If they're waiting indefinitely, then you got an issue, right? You want to get in and get out. And lastly, atomicity. So you want to make sure that your instructions are happening in an atomic way so that they can't really be separated, and they happen without any interruption. Because if you do half of an instruction and then you get preempted, you're going to have a problem there. So those are the 4 conditions for requirements of a critical section. So
I feel like isn't 2 and 3 like pretty much the same?
Yeah, they kind of are. Yeah, this one, I'll be honest, I looked up this one because I didn't really see it in the slides. I mean, there were pieces of it, but he didn't necessarily have 4 blatant requirements.
Maybe, because I feel like those are pretty similar. I would also maybe add as a requirement, like, you must have, like, like an entry code and exit code in order to enter and exit the critical section. Like, that's required to actually have a critical section.
Yeah, I'd agree with that, for sure. Right? If you have an entry but no exit, you don't really have a critical section there. You get stuck in there. Anything else for that?
I can't really think of anything else if anyone else can.
All right. Anyway, so going back to here, right? list 2 reasons why it is a bad idea to implement locks by disabling interrupts. So we went over before that there's a couple of different ways to implement locks, right? They're not the most ideal way, and this is one of them. If we disable interrupts, you're probably thinking, oh, okay, that's great because we don't have to worry about, context switch happening that we don't want. But this creates a lot of problems because there's other things that we need the interrupts for, right? Besides just the context switches that we kind of want to prevent in that case. We miss a lot of hardware events, right? Because hardware events can only be done in the kernel, the operating system itself, and if you turn off all interrupts in general, think of that interrupt vector table, you're missing out on all of that. You're missing out on the good and the bad, so it's not good at all. Also, you can't do this on a multiprocessing system, right? So on a multiprocessing system, on a single processing system, right, you're only dealing with one CPU. If we disable interrupts, it's exclusive to that one CPU. Because of that, that doesn't do anything for a multiple processing system. We're only doing it locally to that current CPU. So this is not a good solution, really. I mean, if you needed something very quick, perhaps, or maybe you wanted to disable all interrupts and have nothing happen, maybe, but this is not good if you just want to lock a critical section. So that's why it's pretty bad. So again, what is a deadlock? If a thread fails to unlock its thread, it creates a deadlock. And all other processes are stuck in that waiting cycle, waiting for that process. And it creates starvation. So it's dead, essentially. That process will just never release that lock, and it's as if someone decided that they are going to just live in the bathroom. Like you have a homeless guy that's just living in the bathroom and just will not give up that key, and everyone else can't use that resource. So, okay, number 9. So we don't really have condition variables on this exam, but it's still good to know, especially for the short answers and for the final, because there's definitely going to be condition variables on the final. So what exactly is a condition variable, and where and why do you need them? So they're a type of signaling variable, very similar to semaphore, right? But they create a specific waiting room for threads, essentially. And it's based on a condition, right? So semaphores are based more either on binary, 0, 1, or counting, which we'll see in a little bit with the H2O problem. And when we need something a little bit more specific than that, we do a condition variable. And we sleep if the condition is false, essentially. So if a condition is false, the wait operation is called until it's notified otherwise. The best way I like to think of this is you and your roommate have an alarm set, right? And the alarm goes off, and it's for your roommate. Your roommate has an 8 a.m. class, and you just want to sleep late. So you get woken up by this. You were notified, right? But that's not your alarm. The alarm was false for you. Literally a false alarm. So you go back to sleep, right? And then once the actual alarm goes on, it notifies you, and then you actually will wake up, and hopefully this is the right alarm, and it's not just your roommate playing a prank on you, and that way you could actually wake up. So this could cause problems, right? Because again, if the wrong alarm wakes up the person, it's kind of annoying. And in the same here with context switches and stuff. But that's why we kind of have that notify all as well. So it's okay, I guess, hey, if I have to wake up, you all have to wake up. But yeah, basically it's more of a specific semaphore. You're using it if you kind of have a specific condition that you want to test for. And you're sleeping until it's true. You're sleeping until that right alarm wakes you up. So hopefully you don't get woken up at 5 in the morning. Yeah, so it's more structured than a semaphore. And this one's very important. Compare and contrast a mutex lock to a binary semaphore in terms of the purpose and ownership. So first things first with ownership, right? The mutex has ownership. Semaphores do not. Make sure that's ingrained in your brain. Because that allows mutexes to have mutual exclusion, right? So that you're only able to have that one thread at a time. You only have that one key. Whoever is in the bathroom is the only one that can get out. So because of that, only the thread that locks in the first place can actually do the unlocking in the end. On the other hand, semaphores, while yes, they can provide some mutual exclusion, they really shouldn't be used for that because of this lack of ownership. Because there's no ownership, this causes a major issue because technically any thread can post and unlock, essentially, that semaphore, so to speak. So with a mutex, right, if someone else tries to unlock it, they can't do it, right? They're not the owner of that mutex. But with semaphores, you're going to see soon that any process can call whatever semaphore it is. So you can essentially unlock the door from the outside in a way with a semaphore. So that's why it's made to provide coordination, right? Coordination and signaling, and not so much mutual exclusion. So that's the main difference between the two, right? Mutex is mutual exclusion. It's done so with its ownership, right? One thread only at a time. Semaphores are more for coordination. It doesn't have ownership, so because of that, a lot of different threads can call the one semaphore. And here we go. This is a good follow-up question. It's not possible for one thread to lock a mutex and another to unlock it. Because again, mutexes have ownership. It makes sure that only the one doing the locking can ever unlock. On the other hand, though, recursive locking is possible with mutex locks. So again, as long as it's the same one that does the locking in the first place, does the unlocking. So semaphores, this is actually not possible. So one negative about semaphores is you can't do recursive locking because how would you keep track of who owns the lock? Semaphores don't have ownership. So another bad thing about semaphores. And the whole point of recursive locking in the first place is a thread that already holds a lock can essentially lock it again. And this happens with recursion, with recursive functions. And you can use the pthread mutex recursive attribute, as we kind of went over before, and it essentially keeps track of the current ownership and the lock count. That way, that same thread that's doing the locking does the unlocking, and it keeps track of how many layers you're on, right? Like one of those the Russian dolls that are inside with one another. You know, that's like you want to keep track of the different layers. And that makes sure that you're able to keep track of how many times it's acquired and released, or locked and unlocked. And usually, right, if some thread already locked, right, another thread would just be blocked. If there's another external thread that's trying to get in, it's still going to be blocked, even with recursive. Recursive is only if that same exact thread calls it again. So if that same thread calls it again, then it will not be blocked, and it'll just increment the counter. So that's just something important to keep in mind. So then we get into priority inversion and its solutions, right? So this part is a little bit confusing, honestly. But essentially, when you have priority inversion, right, we have the bounded and unbounded version, right? And if I just see my notes for a second. Yeah, bounded and unbounded. So the gist of this is that when you have unbounded, when you have just priority inversion in general, right, a lower priority task holds the lock needed to run a higher priority task. So this can create some problems because if this lower priority task runs and it interrupts that higher priority task and it has the lock, now technically a medium priority task can preempt this lower priority task. So it's kind of as if you're trying to go to the bathroom and like your little brother decides to go in, right? And he has the key, you can't get in, but you're supposed to go first because like you're the oldest. And then like your middle sibling goes in because they have a bit of priority over your little brother. And because of that, you're kind of essentially locked out because you're kind of within this layer. There's a higher process that's blocking the lower process that has that resource you need. So that's what we have when we have unbounded priority inversion, right? When it's just bounded priority inversion, so general priority inversion, this is just saying a high priority task is indirectly prevented from running because of that lower priority task. So this is just your little brother took the key and now you can't get in to that critical section bathroom. And something to keep in mind, right? Bounded priority inversion, so just the high and the low, that can't be really helped. You can kind of try to schedule things around it to make sure that it doesn't happen per se, but there's no true solution for it because in the end, it's a scheduling algorithm. And sometimes, if you got priority happening, then higher should be going before lower. But if you have this critical section, then, it has to just run in an atomic process before kind of continuing on. So there's no way to fix bounded priority inversion. You can fix unbounded priority inversion, and this is through the priority ceiling protocol, as well as the priority inheritance protocol. Both of them are very similar in the sense that you kind of try to raise the priority of that lower process to prevent that medium process from getting in there. So it's as if you kind of give permission to your little brother, like, okay, yeah, finish up quick. No one else is allowed here because now he's up to your priority, so to speak. That's how it works with priority inheritance. So it would inherit the same priority as the task that needs that lock. So if you have priority 1 and your little brother has priority 5, your little brother gets priority 1. On the other hand, if it's priority ceiling, let's say you're priority 2 and your little brother gets to the ceiling, which is 1, right? Because 1 is the highest priority. So technically, he can go a little higher than you, in a way. And essentially, this says, at this point, right, whether it's 1, whether it's 2, it's going to be higher than that medium process. And that means that it cannot be preempted, right? We've done a bunch of these problems before in the sense that it would get preempted if there's a higher priority that comes into the queue. Well, if we raise the priority of this crucial process that holds the lock, right, we don't have to worry about any medium length process coming in. So again, we can either assign a priority ceiling level to each resource and lock, and when a task works within the resource lock, its priority level will be boosted to the ceiling value. So no medium tasks can ever preempt it. And otherwise, priority inheritance, and this is boosting the priority temporarily of a task holding a lock. And that's identical to the high priority task. So this is going to inherit the high one that needs the lock. And it's
Your
going to
stream
be...
just ended.
Oh, shoot. Yeah, so did that make sense, right? Just the difference between them. I don't know if he's going to give something like that, but it's still good to keep in mind. Could be a short answer. All right, so that is the end of the short answers. I'll be honest, I didn't really do these parts. So also a lot of these kind of dealt with monitors and stuff, since he had mentioned that there will not be a coordination question. And then the only, I guess, semaphore one is going to be the molecule one. I kind of just, like, abandoned what I had with that and just was like, okay, yeah, let's just kind of do the molecule question. So before we do that, I did want to go over the, I guess you could say, easier version of it, just so you can kind of get the gist of, like, semaphores. I had done a couple of these LeetCode questions, and once you get the gist of it, it's actually really not that bad. And I'm gonna kind of go over a way that we can kind of make it a little easier for ourselves. Okay, so let me just save this in case I screw up. All right, so in this case, right, this is the one that I started off with, and honestly, I'd recommend that you probably do the same, because it kind of just, it goes over the gist of how we even use semaphores in the first place, right? So when we have a case like this, right, we want to print in order, and we want to make sure that the first prints first, the second prints second, and the third prints third. And we can essentially use semaphores for this. And that'll kind of make things a little bit easier for us to, ensure that we actually get things together in the right order, because we can't control that otherwise. We don't know what the what's going to be scheduled or not, So in this case, right, we're not dealing with necessarily a critical section, so we're not going to have to really deal with mutexes. Well, we're just using coordination. So let's just go over very basic semaphores, right? So I'm going to first declare the two semaphores here outside in the global scope. So that's going to be SemT, and I just usually just call it whatever. I mean, you can call it semaphore, you can call it anything you want. I try to make something that makes a little bit of sense to me. So I'm going to just say this is going to be the first semaphore. That brings me from 1 to 2. Actually, 1 to 2. Actually, that caused a problem. Okay. I'll do that, 1 to 2. So this is going to be the semaphore that essentially tells me go from 1 to 2, right? I'm going to also need one to bring me from 2 to 4, to 2 to 3. So sem t 2 to 3. And these are my two that I've created. Now I actually need to initialize these in the first place. So we know that the first is going to run first. So if I were to just block these two from happening, the second and the third, then I'm in good shape, because the only one that it can ever run is going to be that first one. So what I'm going to do here is I'm going to initialize the two, right? So sem init, I'm using this correctly. Yeah, okay. And what I'm going to have here is I'm going to say ampersand, the semaphore name. So I'm going to start out with 1, 2. And then on the other part, right, when we initialize it, there's two parts, right? As Justin said, this second parameter we're always going to keep as 0. So we're just going to assume that, we don't have to worry about sharing this with other threads and processes, so we can leave that alone. But we want to keep in mind that this barrier, we can think of this as a barrier between 1 to 2. We want to keep it locked to start off with. And same thing with the other one, right? Sem init. This is going to be the barrier between 2 to 3. And again, 0 for the second parameter, and then 0 to lock that. If I were to keep this as a 1, if I change that to a 1, this could cause a problem, because now this barrier, so to speak, between 1 and 2 is unlocked, and I can get into either process 1, which has no lock whatsoever, or process 2, which we just unlocked. So we don't want to do that. So we created our semaphores and we initialized them. So at this point, now we're free to actually put them into our problem, right? So we know that the first one is going to run. So I don't want it to wait. I want it to go right into it. I didn't make a semaphore for it, so there's no problem there. But at the end of this one, I need to signal and say when it's done. So after we print the first one, right, we print first, I'm going to do to signal for the second to come into play. And we do this by using post, right? So semaphore post versus semaphore wait, right? So semaphore wait is saying if this is 0, so if this is locked, we're going to wait. Semaphore post is going to essentially add 1 to this resource counter, you could say, and say, now I give you permission to go. It's like handing off the baton to the next process. So at the end of this first function, I'm going to do sem post. And for this, I just need to call the name of the function, semaphore, sorry. So that's going to be the 1 to 2 one. And at this point, it's going to run first by default, which we'll get to in a moment once we fix these two up. It's going to do the function to print, and then it's going to do sem post. So now, this 0 here would get incremented to 1. I'm going to have a signal here, right, to wait until that happens, because I'm going to prevent the second function from happening. So to do that, I'm going to do sem wait, and this is once again the barrier you could think of between 1 to 2. Okay. Now, once again we post to it and we get it incremented, this barrier essentially goes down and it prints the second. Now, I want to, after it finishes that, I want to signal to the third process. And I'm going to do the same exact thing. Sem post, this time to the other semaphore we made, which was the 2 to 3 one. And where does that go? Well, it goes over here. We're going to wait for it over here. Sem wait 2 to 3. So essentially, we're kind of passing on the baton, so to speak, so that we make sure that we start off with the first, because there's no lock, there's no wait that we have to wait for here. Once it's done, we post to the 1, 2, which allows this one to run. Then, once it finishes, I let this run. And then at that point, we are done. So I think I should be good with that. Oh, let's see, what did my stupidity do? Missing a semicolon. We're doing great.
No, it's that you can't have dashes like that in variable names.
Okay. Okay, there we go. All right, so we are accepted, and it makes sure that we run first, second, and third. Nice. All right, so this is basically how semaphores are working, and you can kind of probably see the motivation for this and how it works for the molecules, right? In the sense that we're going to kind of pass on the baton once we get to a certain point. But now we're going to kind of involve a counter to make sure that instead of just it being first, second, third, we're going to get 2 hydrogens and 1 oxygen. Or we'll go on to some other molecules as well, because I've been trying to practice with some others as well. But once you understand the main thing, then it should be pretty simple. So any questions about this before we get started? And oh, nice. We got the Java version too. Yeah, my brain can only handle one language at a time, so too much leak code in a day. Felt that. Questions? Or are we good?
If you don't mind, could you like just briefly explain the weighting and whatnot again?
Absolutely, yeah. So we have two methods when it comes to semaphores. We have wait and we have post. So when we have wait, it's saying if the value of that semaphore is equal to 0, you wait at this point. You get stopped at this point. And this happens over here, right? It says semaphore wait on the semaphore 1, 2. This is initially set to 0 to show that it's locked. So because it's 0, it's going to wait. So if a second function comes in, it gets stuck here and it has to wait until someone uses the post function to essentially increment this guy. This happens with the first function. Right after we print, it uses the post function, and this increments the 1, 2 semaphore by 1. This now becomes 1. Now that it has the value 1, it's essentially kind of like the key that opens this barrier. Now this no longer waits because there's a value in here. There's a 1. But semaphore post increments and semaphore wait decrements. So it's going to pass this barrier, but it can only pass it once, because as soon as it passes this, that semaphore wait is going to decrement it back down to 0. This is very important because it makes sure that only one instance of this function can pass through. Just like when we do the molecule, only one molecule gets passed through. So we print the second, and then just like last time, right, we want to post to the third. So the 2, 3 semaphore, again, is currently initialized to 0. If a third function comes in, it gets stuck here. It's waiting because this was initialized to 0. After the second is done, this post adds 1 to the semaphore and allows this one to proceed, but again, only once, because that wait will decrement it back down. So again, it's like literally you're passing the baton over to that next person. I also like to think of it as if you know like with those construction sites, if they're closing down a lane on 2 sides of traffic, right? And sometimes you have these construction workers that stand on either side trying to coordinate with one another, letting a couple of cars pass by in one direction and then pass in the other direction. So when one stops, the other can go. And when the other one stops, then the first one can go. That's kind of like what we're doing here. So once this first one stops, then that second one can go. Once the second one stops, then the third one can go. On and on and on. And you can kind of create a circle with this too. Like this only prints once, but on some of these others, like printing foobar alternatively, right? As you can see, this is very similar to it, but this time we want to make sure that it prints foobar repeatedly. So just to kind of go over a similar example, right? I initialize these guys. In my class here, right, I have this set as 1 to say that, hey, I want my function foo to go first. So it starts out with a 1 instead of it being 0. So this tells it exactly where I want to start. And this is important because this foo function is going to have a semaphore wait in this case over here. So if this was initialized to 0, then no one can start. You kind of have a deadlock here. Because of this, it decrements here back down to 0, and it prints foo. Now it semaphore post to the B. This is what guides the bar function, which started out as 0. This post increments it by 1, Now I'm over here and I'm waiting for that 1. Once it gets posted, I can proceed. I print bar. Now I post to F. F was decremented by that wait back down to 0. So now, once that's back incremented back to 1, the semaphore wait doesn't have to wait anymore. It can print foo, post, now I can print bar, on and on and on. So you can kind of see how you can go in a circle with this. And this is important when it comes to like repeatedly building molecules, or just even kind of coordinating things to happen on and on and on again. So if probably case 2 would have yeah, you see how it says foo bar, it goes multiple times. So yeah. Okay. Questions before we go on to the actual molecule question? Yeah, so this is actually really not a bad question, honestly. It's a little bit trickier, but we'll kind of get to that in a moment. So let me just put that here in case I need that. So this time, right, we want to essentially print out H2O, right? And you're going to have some input, right, of H's and O's or whatever. It doesn't really matter what the function is. They provide the function for us: release hydrogen, release oxygen. In the actual exam, you're probably not going to have a function, so like you're probably just going to like just say print H or print O. I think that was how he did it in class, so it's the same thing. All you need to know is that each of these prints out either an H or an O. And we want to get it printed so that we have the something crazy like this will actually get printed out as H, H, O, right? So something like this, right? That's the output that we want. So we just want to control the output so we can arrange the string in the right way. So as you can tell, right, similar to the last two, we want to coordinate when these two functions happen. Awesome. So let's start out with our semaphores, right? So like the last one, we want to make sure that this can kind of run on a loop. So in case there's a lot of H's and O's, we want to get it all kind of at the same loop happening. So in this case, we're going to initialize our semaphore. I'm going to need 2 semaphores for this, right? Because I can think of 2 barriers. One between the H's and the O's of a molecule, and then resetting it to go from O to the H of the next molecule. So the way I usually like to think of this is to name the semaphores. I like to think of it as go H to say the H's turn, and then go O to say the oxygen's turn, or whatever your elements are going to be, because he's going to give us something else, and we can go over. I asked AI to build me another molecule, so like there was one with 3 of it. Imagine he gives us something like, yeah, okay, you know what? That's not bad. It really isn't, and I'm going to show you why. It will literally be the exact same thing. I mean, that's a little overkill, but you know what? It's going to have a lot of posts and waits and stuff, but it's still doable. Okay, so this is where it's going to be a little bit different, right? We have our semaphores, but we also need a counter. The last time we only ran each of them for 1 each, right? Foo bar was always going to be foo bar, foo bar. This time I want H, H, O. So I need a counter to keep track of the H. So int H count and that starts out as 0, right? I have no hydrogens. So this is going to help me keep track of how long I can essentially increment before I have to give the turn to O. So now I'm going to use my semaphore initialize, right? So sem init. Again, this is just my preference. And I'm going to first initialize go H. And this time, right? Last time we did 0 and 0, right? This was saying it was essentially locked, right? When we had foobar, we wanted it to be unlocked. We made this a 1. This time, we want this to be the number of hydrogen molecules that we want. So we want 2, because it's H2. We're going to lock the oxygen one, and that will look like that. So for this, right, we initialize this out, and so anytime that we build this class, this one is always going to have 2 to start off with. So if you think about it, last time it was 1, and we were handing that 1 back and forth. This time, we're handing 2 around. So anytime that this guy is running, he gets 2 turns. So hydrogen gets 2 turns, and oxygen initially gets none until hydrogen hands 1 turn to the oxygen. Okay, so we know that hydrogen has to wait for it to have a value. Now, we know that initially, yes, it has a value. But when this kind of loops again, we want to make sure that it's prevented from going until it has a value. So we can't have it just interrupt O at any point. Very similar to with foobar, we had a wait and a post on every single part. So just like before, we're going to do sem wait, and this guy is going to wait for his turn, go H. Okay? Now, at the end of this, right, I know I'm going to need a post. I know at the end I'm going to need to tell this guy, hey, go, oh, it's your turn. Now, what do I have to do in between? Well, I need to keep track of how many of these hydrogens that I have. And this can be done by incrementing our H count. But we have a bit of an issue here. What if 2 threads come in at the same time and they do this at the same time? We could be resulted with a non-deterministic behavior here. This is a need for a critical section. 2 threads can come in and affect this guy, and this could cause an issue, right? So because of that, we're going to need to create a mutex lock here. And before I do that, we want to also say, right, what do we want to do here? We want to say that, right, we only want to release the hydrogen if this H count is below 2, right? So once this is essentially greater than 2, then we would, actually when it's equal to 2, sorry, we would go on to the next step to post. So let me adjust that accordingly. So if H is equal to 2, then we're going to do the post. Okay, so this is essentially how we're going to do it. Let me just double check. I know I just need the mutex. Okay, cool. All right, and then we want to make sure we bring H back down to 0 for the next molecule. All right, but again, as I said before, this can cause a big issue because if 2 threads come in at the same time, we need to make sure that we protect this, and we do that with a mutex. So what we can do is we can create our mutex, right? I'm going to do the same thing here, right? pthread create mutex. Was that the syntax of it? Oh, just mutex t. Shoot. Okay. Okay, I'm thinking of the init function. Okay, so I can just call that M, right? Anything is fine for that. All right, then I'm going to initialize that here, right? That's where I do it. Yeah, okay, that was what I was confused on. Sorry, allergies. Okay,
Bless you, Lauren.
thanks, guys.
Damn, just
See, Justin beat you guys. All right, so now we got. That was great, really great. Okay, so we got pthread, mutex in it. Okay, I just get confused with the thing. This I'm probably gonna write on my hand until I remember it. All right. Anyway, so this one we want to initialize it, right? We want to say the name of it, so at m, and then I just say null pointer. Okay. I think null should also work probably, right? Or no, because you're dealing with pointers, so you want to make sure that's a pointer. I don't think like the like it doesn't like I don't think the professor's gonna be too like stressed about that or anything. So you don't have to worry too much. But essentially, you just want to make sure you declare it. So pthread mutex t, the name of it, and then initialize it. Whoa. So this initializes it, and we're all set to go. Now I can just call my lock function, right? So this is going to be pthread mutex lock at m, and then at the end of the critical section, right? So after we figure all this out and we do our posting, we reset h, all this, now we can unlock it. Pthread mutex unlock at m. Okay. And this is how we're going to ensure that we have hydrogen that's going to work correctly, right? So for this, right, that looks all good. Just to go over it one more time, because I know this could be a little bit confusing, right? We have our semaphore wait and our semaphore post. That should be familiar from the last time. Hydrogen can't go until it has a value, and it can't go on to oxygen until it finishes releasing, right? But we add on the extra part to say, hey, you know, we need to keep track of it as well. And that's what we do with this H++, right? Each time that we're about to release that hydrogen, we increment our H. And once that H gets to 2, then we could post to the next element and just reset for the next part. And again, right, we're incrementing a variable. This variable we declared up here. This is like a global, it's in the scope here. So because of that, it can cause problems. We don't want to accidentally have the wrong count because too many threads came in. So we want to make sure we keep this on lock. So anytime that you have a variable that you're increasing, honestly, like, make sure you have a lock on it. It's better to have a lock than not have a lock. Question: Do we only need at least one mutex even for H2O2C3? So yeah, actually, you can use the same mutex. Semaphores, no, you'd need 2 semaphores for that. Actually, maybe 3. Actually, no, 2. Because 1 in that. Actually, maybe 3. Yeah, 3 for that one. Yeah, you definitely need 3 semaphores for that one. The example that was given in the chat, H2O2C3. We could do that one next, actually. That's a good one to do. But you can use the mutex, right? In the end, only one thing is going to be locked at one time, right? It makes sense because you can only call hydrogen or you can only call oxygen. You can't do both at the same time. They will never be in the critical section at the same time. Now, there could be 2 hydrogen threads at the same time, and that's why we need to make sure, critical section stays locked. But these functions are going to run kind of mutually exclusive from each other because of the semaphores. So the semaphores keep us from calling different functions at the same time. The mutex prevents us from adjusting the critical section at the same time. So let's finish off with oxygen, get this submitted, and then I'm gonna do the same thing for the H2O2C3, and yeah. Okay, cool. So just like before, right, oxygen this time, oxygen's only releasing 1. So this kind of makes our life a little easier in the sense that I don't need a counter, I don't need a mutex, I don't need anything there. Just keep it simple. I need to just have my weight, sem weight. And what am I waiting for? I'm waiting for my turn. I'm waiting for go O. Okay? So this is going to go O. It's going to release the oxygen. Then I need to post. But here's the thing. Remember when I said that post also adds 1 to my counter, right? My counter for my semaphore. I have to make sure that not only am I saying, okay, H, it's your turn, but I have to give it the correct number of turns. This next one will need to run twice. I have to call post twice. And this is just simple. I just have the same exact line of code again. So that would be for that. And I think that would be it. Nope. Okay. What did I do this time? Oh, because I said H count and then that's just H. You know what? I use that more often. Okay. I promise you guys I can code correctly. Yay! It works! Okay, so questions about this one? Because otherwise we'll adjust the code for this example here. And you'll see it's literally, as Justin said, like boilerplate. You're literally using the same template, but you're going to just adjust it accordingly. So, right, we did... Okay, I'm not going to be able to run this because, it's meant for this condition, and I can't get my VS Code to work with these semaphores and stuff because I think a lot of these, like this init is like deprecated for some reason, so I don't think it's like the newest version or something, so it's a pain. So I'm not going to be able to test it out, but if this works, then the same thing should work for that too. So I could just do it on there. I also kind of pulled it through AI as well. So AI seemed to say that it went through. So I think we should be okay with that. I did a similar question for some other element. I think AI was more concerned that it wasn't a real element than my actual code, but that's besides the point. Anyway, so last time we had H and we had go H and go O. This time, though, we have a third molecule, right? So instead of H2O, I'm going to have, I'm just going to write it up here. We're going to have H2O2C3, right? This is the one that we're dealing with this time. So I'm not going to adjust the other stuff. We're just going to deal with the semaphores and mutexes and all that. But for this case, right, we're going to have 2 hydrogens, so that part stays the same, 2 oxygens, that we need to increase a bit, and 3 carbons. So this time I have go H, go O. I'm going to need also one for go C. So I like to call it this because it kind of tells me where I'm going. Like this is clearly telling me where I'm going and I can kind of go accordingly from that. Honestly, when he did the bounded buffer project, the at empty and at full was kind of throwing me off, so name it something that makes sense for you. All right, so now we also need a counter for the others as well. So int O is equal to 0, and int C is equal to 3. So we're going to have counters for all three of these guys now, because now we're dealing with all these are greater than 1, so we need counters for them. All right, I'm going to make one more initialized call, sem init, go C, 0, 0. Because again, we're not starting with C, so that part doesn't change. Our one mutex is enough. That's totally fine. So this part, hydrogen is exactly the same, right? H2, that stays the same. Oxygen is where things are going to change up a little bit, right? So in this case, right, we wait. That's totally fine. Now over here, we're going to have to do the same thing. We're going to increment O as well. And this is right before we release our oxygen. Now what I'm going to end up doing is I want to make sure that I'm only going to go on to the next part when it's equal to 2, because I need 2 oxygens. So once this runs twice, my counter will go up. So if O is equal to 2, then go on to my next part and say I can do the posting. But we made ourselves a critical section here. If too many threads come through, this can easily get skewed and we can get the wrong number. So because of that, we need to create our mutex over here. So we're going to do our pthread mutex lock at m, and I'm lazy, I'm copying and pasting this. And after this line, I'm going to do the same thing, and I'm just going to say unlock. Okay. All right, so kind of same situation here. And I keep forgetting to reset the value, of course. So we want to make sure that we reset it for the next molecule, so O equals 0. Now, one last thing though. We want to make sure that this can get ran in the first place. We only posted once to it in the hydrogen function. I'm going to need to post a second time in order to give it enough turns to actually be able to go twice. So just like that, I changed this by adding a second post. Everything else in hydrogen stays the same. For oxygen, I did the same process that I did in hydrogen. I created my mutex lock over here, and that lets me increment my O counter safely, release the oxygen each time, and test, hey, if this is equal to 2, then you post twice to the next atom. This time is going to be to carbon, so it's not going to go back to hydrogen just yet. All right, and then the last part is we want to create the carbon atom as well. So we're going to have this. I'm going to just copy it just to save some time because it's exactly the same process, right? This time we'd have carbon, release carbon over here. This time though, it's waiting on go C. I'm once again going to have to lock to increment my carbon counter. I'm going to change my function. This time though, carbon has to be 3. So what are we changing? If C is equal to 3, then I go to my next atom. Well, it brings me back to hydrogen. So I need to go H twice. Give H its turn twice. And then reset C equal to 0. And unlock my thing there. And I just did that on the wrong function, didn't I? Good job, Lauren. Okay, yeah. Well, I said the right thing, but I did it on the wrong function. So, yikes. Okay. Again, going back to hydrogen this time. C is equal to 0, and that should be good. Okay, so again, I can't really run this because, it's on leak code, and this is definitely not the problem, but this would be how we'd solve it. So we did the boilerplate for it, and yeah, that's kind of pretty much what we just adjusted it for. So all we did was we created another semaphore to handle the other barrier, right? Because now we have another molecule to deal with. And then we have, we initialized our counters because now we have a lot more to count. We created our semaphores over here, initialized them all. Again, H went first, that was S2. These are kept as 0 to keep them locked. We have our mutex. And hydrogen was just changed to go O twice. I did a 0 there by accident. I think my brain is fried. And that's only happening if H is 2. So just like before, you need 2 hydrogens, your counter to be 2. In order for that to happen, reset, our mutex finishes. Now we're in oxygen. Oxygen, instead of 1, it's going to be 2. So because of that, we are going to do the same exact process. Have our mutex, increment each time we release when it's equal to 2. Then we go on to the next atom, which is carbon, and put our counter back to 0. Carbon, same thing, right? We wait on our past atom to finish. Then over here, we have our mutex, right? Increment each time we release. If C is equal to, that's supposed to be 3. Yeah, because there's 3 atoms of carbon. Then I can post to that. And wait, it's supposed to be 3. Okay, I think that got messed up. So we want to make sure that we post the number of times that we're going to go. So carbon has 3. I post 3 times. On the other hand, hydrogen only has 2. So then we're only going to give hydrogen 2 postings. And this is how we do that. So I'll post this in the chat. And then this is my code for the original H2O1. Yeah, so you're welcome to play around with it. If you can get it to work on your VS Code, great. I was not going to fight with it. But as far as I know with LeetCode, it's good. And also this is the way that he went over it in class as well. So yeah, we're all good. Essentially just remember the pattern for it. Know your weights and your posts and how to kind of coordinate between it, and you should be good.
Lauren,
Mhm.
quick question.
What's
So
up?
when you initialize the semaphore go H, right?
Mhm.
So the parameter is 2. Why is it 2 again?
Great question. So this is the initial value that it starts off with. You can think of it as the number of turns that GoH has. So this allows only 2 threads that have the GoH function to pass through. Because each time it passes through, what do we have here? We have a semaphore weight. And this decrements it each time. Remember, it's a counting semaphore. So each time it passes through this point, it decrements it by 1. So after 2 threads pass through here, this will go back to 0 and it will wait on this point, right? So the semaphores make sure that we have the right number of threads passing through. And once that happens, right, once H is equal to 2, only then we're allowed to do this part. And just like before, right, we post a few times right here. The reason we post twice is because that adds 2 to the counter of O. So it was initially 0, but at the end of this part over here, this 0 would become 2, and this 2 became 0. So it kind of just tells us how many we're allowed to pass through. Does that make sense?
Makes sense. Thank you so much.
No problem. Other questions? All your brains are fried? Okay. Yeah, so that's kind of the end. Justin, I don't think there's really much else, right? We kind of covered everything, right?
I mean, that should be it, unless there's anything anyone else would like to cover, that we didn't cover, or you just want like extra clarification over a specific topic. Like if you guys wanted to go over some thread code or something, we can do that maybe. But whatever y'all want to do, I'm fine with. Can I go over you? If you get over a 90, sure.
Oh.
You guys think something like 17 would be on the test? 17 on which problem set? Process synchronization, number 17. No, I doubt it. I don't even know what I'm looking at. I haven't read this, but I highly doubt it.
Yeah.
Because, like he was saying in the first, like the reason he took out coordination is because he was like, oh, we wouldn't even have enough time because of all the coding problems we already have. So the synchronization, the scheduling stuff on top of the 2 coding problems, we wouldn't have enough time to do that in a short answer problem. Like, there's no way.
Yeah, literally the only coding that you need to worry about is the molecule question and the thread question. So the molecule question, it's literally going to be like identical to the, honestly, like that one that we just did, that 3-1. It's going to be something like that, but just different letters and numbers, but it doesn't really matter. It's the same thing. And then the thread question will probably be one of those 3 that we kind of went over, or very similar to it. I mean, it's the same exact boilerplate again. It's just the function itself is different.
Yeah. And again, like Lauren said, and like I said, it's the molecule stuff is just boilerplate. Like, you just change what you're doing based on like the actual input, I guess. So I feel like that's pretty much free points. It's 18 points. You just gotta memorize that boilerplate code. Process scheduling is pretty free as well. I think that's what, 35 points or something like that.
Yeah.
So the main thing you guys just need to focus on is the thread stuff, which thread code, we're not guaranteed to know what the problem will be. It won't be necessarily hard. You just need to remember like the kinks of it, like, using a global data structure to send data from the resulting thread to main, or just things like that. You just need to be able to identify that, because the problem that he'll give for the threads won't be that hard. Like it would be like an easier version of a LeetCode Easy, basically.
Yeah,
and then for the short answer, that's just fair game. Like, I would just read through it. I still haven't looked at all the short answers too, so after this, I'm gonna hop off and try to answer some more, but I'll see.
Yeah, no, I definitely agree with that. I would really recommend, like, if you're kind of worried about the coding, focus a lot on the process scheduling and the short answers, because that's kind of like a given. I think the process scheduling is a little on the easier side, and then short answers, like, you're just memorizing the stuff that we're doing, so.
Yeah, good point.
Yeah, I think I mean, honestly, I think the molecule question might be easier because we kind of know exactly how it's going to be done. You know, it's going to be literally that exact thing. The only thing you're updating literally is going to be just the number of posts and weights and the counters and everything. The thread might be just slightly more involved, but oh my gosh, it's Oliver!
I'm gonna say hello.
The code for all
Yeah, I
mascot.
think at most he'll probably give like 3 or 4 like elements in the molecule, and then he'll just change the number. So at that point, you're just changing the number of the number of weights in post. That's literally it, just like Lauren said.
Yeah, exactly.
I remember Akinlar saying pseudocode is fine. Yeah, he said that for the first exam too, but then during the exam he said it wasn't, so I wouldn't trust that. I would be careful with that.
Alright,
Because I asked him during the first exam and he was like, no, yes, it has to be like syntactically like C or Java, so
I'm gonna stop the recording here.